Before we look at phase sensitive detection as such, I want to talk about something called amplitude modulation. Okay, and develop some concepts that would be helpful for us as when we go and detect phase sensitive detectors as such. Okay, so here, so think of the circuits, the bridge circuits, or any other sensors or signal conditioning circuits for reactive sensors that we have discussed before. So we had an input, and let's call it VE, which is a sine wave, and then you have X, which in the previous video we said, oh, let's assume X is a constant; it's not really changing, but in reality, X would be changing, right? And let's assume that the change in X is a sinusoidal shape. So what is the output going to be? In the case of a single sensor, that is a sensor which is not differential, we'll have V naught equal to VE 1 plus X over 2. And we have kind of ignored the X in the denominator here. And if you multiply both these signals and if the output is dependent on this equation, then you get a signal like this. Okay, so can you see that the amplitude of the sine wave here is varying along with, in the same shape as X is varying. Now we are assuming here that the change in X is much slower than the change in the input signal to the bridge or to the voltage divider. Okay, and that is one of the considerations that we'll have to keep in mind. uh, your the frequency of this signal needs to be much higher than the frequency of the change in physical quantity that we are trying to measure. Okay, so this process uh, of getting the output from the inputs, okay, and I'm calling this also an input because this is an input, the physical quantity. This is an amplitude modulated signal. Now, if you look at this signal very carefully and look at it in the frequency domain, what you would see is this is a sinusoid of a particular frequency, right? So in the frequency domain, so here in the x-axis we have frequency, I can just plot it as one impulse at the frequency fc, let's say. So the frequency of the signal is fc as shown here, and the amplitude is ve. So just based on the ve and fc, I can plot this sinusoid like this. At the same time, I can plot this um, change in physical quantity, or this x, as well on the frequency domain, again with the same with one impulse, but this impulse will be at frequency fs, which is much lower than fc, and an amplitude of x, let's say. So what happens when you amplitude modulate? What happens to the output of the sensor? We've looked at the output of the sensor, and we've said the output is basically VE 1 plus X over 2. So you can write it like this, and you can do some mathematics, and you get a sinusoid like this, or not a sinusoid, a signal like this. Now this signal will have us. So I'll leave you to work through the equations on the previous slide. And what you would see when you do that is you have look at this. This is the output, and what you get is you have a signal at frequency fc. You have some amplitude at frequency fc, and it at fc the amplitude of the signal is v over 2. So fc, so there's a spike at v over 2, and at fc minus fs and fc plus fs, you have an amplitude of vex over 4. So there are two more points on the signal. So what amplitude modulation has done is it's taken your signal at fc, okay, and then it has given you two signals that are proportional to the x on both sides of this of the carrier signal, of the input. Okay, so usually what we do is we call this ve signal, the input to your bridge or the input to your signal conditioning circuit, as the carrier signal, and x as the message signal. So we have two points on both sides of the carrier signal that carry the information of about X that we want to get. Okay, so this is the case when we have single sensors, not differential sensors. What happens when we have a differential sensor? So again, you have the carrier wave, which is the input to your bridge circuit, to your signal conditioning circuit, and you have the message signal, which carries the information about the physical quantity, which is X, and the output in the case of a differential sensor is VEX/2, and so the signal looks like this. Okay, now let's look at the frequency domain representation. So in the frequency domain, if you look at it, uh, so it looks like this. Okay, so you have a spike at Fc minus Fs and with this amplitude, and at Fc plus Fs with this amplitude, but there is no signal at the carrier itself. Okay, so this kind of signal is called this kind of amplitude modulation is called double-sided, because you have peaks at both sides of the carrier signal, but carrier is suppressed. So double-sided, double sideband, carrier suppressed amplitude modulation. Does that make sense? So double-sided, but the carrier is suppressed. Okay, in the previous case, when we looked at this, here the carrier is not suppressed, so we say carrier transmitted. So double sideband, carrier transmitted amplitude modulation. Now, one of the reasons why you use transmission and suppression terms is because amplitude modulation is also used in communications. But right now we are looking at the same concepts, but in a sensor domain. Okay. So in a single sensor, the output of the sensor looks like this. In a differential sensor, the output looks like this. Okay. So with a single sensor, you have double sideband transmitted carrier signal. And in a differential sensor, what you get is a double sideband suppressed carrier signal. And what you can, and if you rectify the signals, what you can see is, if you rectify basically means that you have removed the negative part, or you have switched the negative part into the positive side. You can see that you can see the message signal here still, right? So if you detect the amplitude of the signal, you'll get the X out. But in this case, you have lost the message signal. Can you see? You're not getting the X anymore, like this kind of a sine wave. You're getting some strange kind of signal. So you've lost the phase information. So basically what I'm saying is you lose the phase information only in case of differential sensors. You do not lose the phase information in the case of single sensors. So that's another disadvantage to differential sensors. But then differential sensors have other advantages that we want to keep, like increased sensitivity, linearity, and things of that kind. So how do you actually recover the phase information in a differential sensor? So phase is lost. There is no difference between X and minus X, right? You can see that there is a difference between X and minus X here. So here you have this sine wave when you have X, and you have a different sine wave, a different amplitude shape when you have minus X. But in this case, you can see X and minus X have no difference. The signals look exactly the same. So the phase is lost. So in the next video, we'll look at how we can recover our phase information even for differential sensors.